All right. Hi, everyone. Welcome to the online ubermag tutorial. This is Xinfan from University of Denver. This tutorial series are organized by Kirill Belashenko from University of Nebraska and me, sponsored by the IEEE Magnetic Society. The goal of this tutorial series is to bring useful and important knowledges on magnetism to everyone around the world. When we were organizing the OOMMF tutorial, Dr. Mike Donoghue suggests ubermag. Ubermag is a Python-based framework that can drive both OOMMF and MUMAX with nearly the same code. So it is a natural sequel to the online OOMMF tutorial. We reached out to Dr. Marianne Beck from University of Southampton, who's a co-developer of ubermag. I'm very grateful that he agrees to give this tutorial with Professor Hans Fangohr and Dr. Ryan Pepper from Southampton moderating the session. So there will be 3 sessions of ubermag tutorial, and today is the first episode. Dr. Marian Beck graduated microelectronics from the University of Novi Sad in Serbia in 2010, and then obtained a master's degree from the University of Southampton in UK in 2011. He was a postgraduate research student at the Institute for Complex Systems Simulation Doctoral Training Center at the University of Southampton, and was awarded a PhD degree in 2016 with Skyrmionics states in confined highly magnetic nanostructures thesis. After obtaining PhD, he worked as a research fellow at the University of Southampton until September 2017, when he moved to the European X-ray Free Electron Laser Facility, XFEL, in Germany. At the European XFEL, he was employed as a computational scientist until August 2019, working on the OpenDreamKit Horizon 2020 European Research Infrastructure Project, which brought together a range of projects and software to create and strengthen virtual research environment. From October 2019, he is employed full-time as a senior research fellow at the University of Southampton on the EPSRC Skyrmionics project. His main research interests are micromagnetics, computational science and engineering, development of finite element and finite difference, micromagnetic simulation tools, magnetic skyrmions, block points, complex systems, reproducibility, and data analysis. So many of you have attended the OOMMF tutorial, so you already know the drill, but let me reiterate how we will carry out the tutorial. First of all participants should be muted and kept the camera off to save bandwidth. If you have any question during the session, please send those questions as private messages to the moderators. The moderators will answer some of the questions directly. For those that will be discussing during the tutorial, they will compile the questions and send them to the lecturer, Dr. Beck. If you click the participants button at the bottom of the screen, you can see a list of participants. The 2 moderators, Professor Hans Fangohr and Dr. Ryan Pepper, will be on the top of the list with moderators next to their names. You will also notice a thumbs up symbol next to the moderator's names. That means that he is taking questions. If there's a thumbs down, it means the moderator is busy. Then please send the question to the other moderator with thumb up emoji. Please only send a private message to one of the moderators. Don't send message to all. If you have any technical difficulty, please send to Professor Kirill Belashenko. His name is also at the top of the participants list. And for people watching this on Twitch, you can type questions in the chat box at any time. You will have to register with Twitch in order to be able to do that, by the way. Due to a large size of participants, we may not be able to answer all questions live. Future questions can be asked and answered in the GitHub group, which will be announced to you by Dr. Beck later. So without further ado, we just want to welcome Dr. Marianne Beck to give this a very exciting tutorial.
Okay, thank you, Shin. So I'm Marian. You heard a little bit about me now, and yeah, I think we start with what we prepared for today. So first, a little bit about the organization. Before we start, I'd like to acknowledge the IEEE Magnetic Society support, and as well Xinfan and Kirill Belashenko for organizing the workshop. I know it wasn't easy. There are many administrative questions. So the people in the workshop are myself, so Marianne Bag, and we have 2 people available in Zoom. You can ask questions, you can send your questions to them. They're Ryan Pepper and Hans Fangohr. Shin already mentioned that. Here, just once more to reiterate how the questions are going to work. So there are basically 2 ways how you can ask a question. Number 1 is you raise an issue in the workshop repository. I'm going to give you a quick tour in a few minutes of the repository and how to do that. One thing to be careful about that is that the questions and answers you write there are available to anyone. So anybody who opens the repository can see your questions. So please don't post anything too personal or any confidential research related information. And also those issues are usually searchable by Google. So just to be careful about what you write there. And during live sessions, send your questions as a private message on Zoom to either Hans or Ryan. And if you are on Twitch, you send your question there and we're going to find it. Now, due to the large number of participants and the limited time of these sessions, we are most probably not going to be able to answer all questions. So if at the end of the session, your question is not answered, you please go to step 1, this one here, and raise an issue in the workshop repository. And yeah, then we can see your questions and answer it there. Now, if you see any questions on GitHub that you think you can answer yourself, please do. So the questions are not only for us. Please feel free that you all communicate among yourselves. So yeah. Now, the sessions, as you probably know, we're going to have 3 sessions each Thursday starting today for 3 weeks. And for each session, we gave the approximate topics we're going to focus on. However, it is very difficult to divide it like this because everything is bundled together. So probably certainly each session we're going to be covering a little bit of everything, but you can consider these 3 topics to be like what the main focus is going to be. So each session, a little bit of micromagnetics, Jupyter, Python, and ubermag, just at different levels. So today we start with real basics. What is the aim? So from the survey, we saw that the majority of participants are PhD students, and most people never ran a micromagnetic simulation before. Now, I assume that most of you attended the OOMMF tutorial by Mike Donahue, so you are now a little bit familiar with micromagnetics and simulations. You can run OOMMF. But for ubermag, we're going to start a little bit from the beginning as well. And our goal is to establish a good foundation so that at the end of the workshop, you are able to set up and run your own simulation in ubermag. You can analyze and visualize the data. And then we're going to teach you some tricks, how you can read the documentation, how to understand the API references, so that you can, after this workshop, if you want to, and when you need to, you can go to documentation, understand it, and learn more advanced topics on your own. Now, what do you need for the workshop? I'm going to show you this in a second, but quickly to go through slides. Through this slide. So the workshop repository is on GitHub. This is the URL, so github.com/ubermag/workshop. And all the materials we make during this workshop, so slides, tutorials, exercises, questions, anything is going to be there. In addition to that, there is a README section on the repository where we're going to keep all the information up to date. So when you're not sure about something, this is the first place you go to check what to do. Now, second thing is how to run ubermag. You can obviously install it on your machine. we made a few YouTube videos. I'm going to show that to you soon, how to install it on your operating system. But if you don't want to install it, or you can't install it, or for any reason, you can run it in the cloud via Binder. Few things here. Binder is a free shared service, so it's sometimes it takes a few minutes to start a session. So please be patient. So if you wait for 5-6 minutes, yeah, it's sometimes it's really quick within 5-10 seconds, but sometimes it takes a bit longer. Nothing is wrong. You just have to wait a little bit. And when you are on Binder, after 10-15 minutes of inactivity, the Binder closes itself. But I'll show you that soon. And the last piece of information is that we've noticed that the most recent update of Safari on macOS sometimes does not interpret colors well, and there are some problems with widgets we use in notebooks, and that's why we recommend using the most robust browser of the Google Chrome. Quickly about the installation. So ubermag is a Python package, and for those people who are familiar with Python, you can install it in many different ways. You can use pip, miniconda, anaconda, navigator. You can use it via Docker. In the beginning, so for today, we're going to focus on miniconda, which is actually our recommended installation. Two things you need to do there is, one is to install miniconda, and then to install ubermag using miniconda. The detailed instructions you can find in YouTube videos. And as Shin mentioned, so the idea of ubermag is to have a unified interface to both OOMMF and MUMAX. However, because of the lockdown and everything, we have a very limited access to GPU machines. So during this workshop, we're going to be focusing on OOMMF. And my plan is that in the last session, so in the third session, I showed you one example with MUMAX. The idea is that interface is exactly the same. So by learning ubermag for OOMMF, you are automatically learning ubermag for MUMAX. MUMAX 3 is currently available from the development branch if you want to install it. And as I said, I plan to show it in the last session. And yeah, probably by then I'm going to make a release, and it's going to be much easier for you to install it. Yeah, then let me now go to my browser. Yeah, I hope you can see my browser. So here, this is the workshop repository. The URL, as I said, github.com/ubermag/workshop. That link is in the slides that are already here in the repository. Now, when you open it, you're going to see this, but when you scroll a little bit down, here is a README section. And in the README section, these two badges are actually probably the most important for now. This is the Binder. So when you click on this link, you're going to open a Binder session, and Binder session is, yeah, I was inactive for too long. Let me just open it again. Yeah, we'll wait for a little for open. And this one is the YouTube channel, and on a YouTube channel you can wait a little bit. Oh, sorry, the Zoom covered my top. Okay, here. So this is the YouTube channel. At the moment we have 3 videos how to install ubermag on your machine for 3 operating systems. So if you follow the instructions in here, it shows you from scratch how to download miniconda, what to run. In the future, we plan to make videos for different installation types, like Anaconda Navigator, which with it you don't have to type any commands in command prompt. You can do everything by clicking. And then a little bit more advanced installations using Docker so that you can use some Linux extensions we have for OOMMF on Windows machines. Now, by installing ubermag using Miniconda, everything is automatically installed. So even OOMMF, for example, so you don't need to install it separately. It's going to pull it from the cloud depending on your operating system and install it. So you don't need to teach ubermag how to find OOMMF. You don't have to compile it. So everything should be there automatically. So we said binder. Okay, binder is now open. So when you open binder, you're going to get this. Here are going to be the notebooks that we're going to go through each session. Today, my plan is to have only 2 notebooks. Even that is probably too ambitious because we have a lot of slides. And you click on one of those and it's going to open the notebooks we're going to go through. It's intuitive, but I'm going to show you that when we go to notebooks actually. Now, information, what to do before the workshop, materials, yes. Materials are going to be here. So you can see there are different directories. In slides directory, there is a slides PDF. I'm always going to put a PDF file here because I want everybody should be able to open it and to keep it of a reasonable size. If anybody wants a full presentation file from Keynote where we have movies and animations, then let me know and I'll find a way to share them with you. Now, how to download. So you don't need to know Git at all or to clone the repository. You simply click on the slides and here on download, and it's going to download a PDF of the slides. That is the same for any file you find in the workshop. Now, in the tutorials, I'm going to put the notebooks. We're going to go through each session. And these are actually the notebooks you see when you open Binder. And final thing, a little bit extras here. Here we put the materials that don't belong anywhere else. So here I left a few questions from the last sessions. Somebody might find it useful. But yeah, I will refer to it when necessary. Oops. Now, the last thing is asking questions. So here in the repository, there is this issues tab. At the moment, we have no questions. To ask a question, you click here on a new issue. And here you type the title of your question. So let's call it a test question. And here you ask something. Now there are labels here. You can choose some of the labels if you want to, just for you and for everybody else to make it easier to navigate. So if you have a Jupyter question, installation, general question, if you found a bug, Python question or anything, and then you click here on a submit new issue. And now the question is there and we get an email each time you post a question and we answer that here. Now, how do you know the question is answered? By default, I'm not sure what happens, but here you have the settings for watching the repository. So I think by default, you are going to be in releases only. So that means that when somebody mentions you directly or replies to your question or continues the conversation, you are going to get an email. If you don't want to get anything, then you can say that you're ignoring so you don't get any emails. Few things I forgot to mention is that everything in the repository you can see and download, but if you want to ask questions, you're going to need a GitHub account. So please create one. If you're going to ask questions, it's really easy. It takes, I say, less than a minute to do it. Okay, so now I guess we can go back to the slides. Okay. So I hope you can see my slides now. Okay, so the plan for...
Maria, we
Yeah.
haven't seen your slides yet.
Oh, okay.
You may have to click share slides again.
Yeah, let me just try it again. Okay, my mistake. Working now?
Yes.
Good. So the aim for today is to get some basic understandings of micromagnetics and hopefully write our first ubermag simulation. So at the end of the session, you should be able to write a simple simulation. Our assumption is that you have no previous experience in micromagnetics, Python, or Jupyter. So you shouldn't worry if you don't know Python. In my opinion, you don't even need to know too much Python to write simulations because it's pretty repetitive and there are certain patterns. Of course, more you know Python, more effective you are in using ubermag, but it's not an absolute must. And today we're going to cover a little bit of Python. So today, all the basics, micromagnetics, Python, and Jupyter, and hopefully we're going to do the first ubermag simulation. So let me start now with micromagnetics part. So micromagnetics, what is it? It's a field of physics dealing with the prediction of magnetic behaviors at sub-micrometer length scales. The source of this is Wikipedia, so when I need some catchy definitions, this is the place I go to. Now, the magnetization field. So magnetization field is basically the main unknown we want to find. So we are doing the simulations in order to find what M is. In micromagnetics, magnetization is a continuous vector field. And in general, it is a function of both space and time. Now, in micromagnetics, there are certain micromagnetic assumptions that we always have to think about when we do simulations. So the first one is that the magnetization, as I said, a vector field is differentiable because you're going to see in equations we have a lot of derivatives, so we want M to be nice and smooth. So we want it to be continuous and slowly changing with respect to both space and time. Another assumption is that the norm is constant, so the length of vector M doesn't change over time. This means that micromagnetics is basically zero temperature. Constant norm that doesn't change over time is represented by saturation magnetization, and we write it as MS. And as I said, we assume it's constant. Now, you can say, okay, does it mean that can it vary in spaces if you have two different materials? Yeah, I would say yes, but we assume it doesn't vary in time. Now, the magnetization I showed you, capital M, is usually represented by a normalized magnetization. Just because we don't like large numbers, we want to think about the magnetization components to be between -1 and 1. So in this presentation, we're going to have a look mostly at lowercase m, which is a normalized m. So the full vector field divided by saturation magnetization. And this is an obvious assumption. Now, the discretization. In order to solve the magnetization numerically, we said it's continuous vector field, but to be able to place it in computer memory, we have to divide the whole domain into small chunks. Now, there are two main ways how we can discretize the space, the field. There are finite differences, finite elements. Finite differences such as OOMMF, FIDIMAG, MUMAX, finite elements, FINMAG, NMAG. And there are generally two rules on how to choose the discretization. We're going to look into more details later. So discretization must be large enough so that we can ignore the We can ignore the crystal structure of the material because, as we said, we're working continuous approximation, but it must be small enough so that we can spatially resolve the features in the field that we expect to see. Now, a little bit on finite difference discretization. So this is our magnetic sample here on the left. And as I said, we divide it into small chunks. In finite differences, those are small cubes. Now, when we zoom in one of those cubes, inside that cube, we actually have a bunch of atoms. And this is a unit cell of a crystal structure. In my case, it's some simple cubic one. And now, inside this entire volume of the discretization cell, if I sum all those magnetic moments of individual atoms and I divide by the volume, I get a magnetization vector M. And this is a vector I assign to this discretization cell. So each discretization cell in our sample has one vector assigned to it. And we assume that that vector doesn't vary inside a certain cell. So whenever you are in one cell, it's always the same. You think about it like that. So magnetization field, as I said, vector field, and yeah, discretized. Here now, this is basically, I already said that, but here I just wanted to make it a little bit more obvious. So this is our sample. We divide it into small cubes. Each cube has a single vector in it. And yeah, basically a vector field are three scalar fields, mx, my, and mz. Now let's look a little bit into energies. So we know what the magnetization is. So magnetization, we now think about is it's a vector field, which is a function of both position and time. And for each magnetization configuration in the sample, we can compute the energy of the system. Now, the energy equation is basically a mapping of magnetization field to the energy density, which is a scalar field. And at the energy density, we can think about it as a sum of individual terms. So let's say one term can be exchange, another term can be anisotropy, third term can be DMAG. So we think about the energy equation as a sum of individual energy density terms. And this is something that you as a user or as a physicist must decide what is in my material, what are the right parameters. So this is a modeling part, and you should know what to model. Now, as I said, energy equation takes a vector field and spits out a scalar field. And now we take that scalar field and integrate it over the whole volume. We get an energy functional, or again, we get a single number, and that's the energy of our system. And now in black boxes, as I like to think about these problems, we're going to look at the algorithm in the end. From our magnetization M, which is a vector field, we stick M into each of our energy terms, get the sum, and we get the energy density. Energy density, as I said, is a scalar field, and it's also a function of space. And then if we integrate that scalar field over the entire volume, we get a single number, which is an energy, which is the energy. Now let's have a look at all the individual energies quickly, and with a few warnings what to be careful about when you write simulations. So the first and probably the simplest one is the Zeeman energy term. What does it want to do? It wants to align the magnetization M parallel to H. So H is an external applied field. And if we have, this is, let's call it, can we call it a spin or a magnetic moment, or I don't know, we're not in atomistic simulation, but let's call it, yeah, magnetic moment. So this is an M vector at a single cell in our sample. So this is the M, and this is the applied external field. And now what this energy wants to do is to align M parallel to the field, obviously. Now, the parameter you need for this energy is H in amps per meter. And this is very important. So the parameter is not B, it's actually H. So ubermag expects you to give a number. And then if you put a B of 0.1 Tesla, it's going to think it's actually 0.1 amps per meter. And you won't see anything happening in your simulation. How do we compute it? Pretty easy. Minus dot product of two vectors, M and B, but usually we rewrite it in this form because M is ms times lowercase m and B is mu naught H. And now here is a quick animation. So if we have 10 discretization cells or 10 atoms, think about it however you want, and we apply field in the up direction, let's say positive Z direction. And here on the side, we see the side view. So this mess here is basically if we look at these arrows from this side here, from the left. So if I run this is actually a real simulation we get from ubermag with no precession, just damping, just to make it quick. You see, we start from a random state, apply the field, and all magnetic moments apply parallel to the field. Now, uniaxial anisotropy, what does it want to do? So let's first have a look at the equation, maybe. So this is the formula, minus k m dot u squared. The assumptions, important assumptions, are that the norm of m is 1 and the norm of u is 1. So they're unit vectors. And here's this minus k in the front. So because norm of m and norm of u is 1, when you do the dot product, we can write it as a cosine squared. And cosine squared is 1 minus sine squared. And then when we multiply with k, we get something like this. So when you look at papers, you usually see all of these forms, and it can be confusing because of the sign in front. So it's minus k dot product minus k cosine squared, but it's plus k sine squared. This we usually ignore because we think of the energy like a potential energy in mechanics. So we choose the reference level we want. So we ignore this. So you can see with many signs in front. Now, why is this important? Now, if we think about this formula here, we think about it, when is this minimum? So when is the energy at its minimum? It's at its minimum when, so it's minus something. So we expect this something to be at its maximum. And the maximum is at when m dot u is, m and u are collinear. So when their dot product is 1. So that means that if k is positive, like here, so if we start, this is the anisotropy axis, and this is the magnetic moment. If k is positive, we're going to get m aligned with a b along the anisotropy axis. Now, if k is negative, when it is going to be minimum when m dot u is 0, and that means when m and u are perpendicular. So depending on the sign of k you put in your simulations, you can change the character of uniaxial anisotropy. It can be either easy plane or it can be easy axis. Now, quickly, just to demonstrate to you what it means. Yeah, I forgot to say the parameter for anisotropy is k in joules per meter cubed, and an anisotropy axis, lowercase u, which is a vector. And again, if we start from a random configuration over some time, magnetic moments are going to be either up or down. And here is the side view. For easy plane, now we choose the negative k, and when we run the simulation, we're going to get all magnetic moments be in plane. So they're running from this anisotropy axis u. Then there is a cubic anisotropy. That's very quickly. We don't use this very often. So in uniaxial anisotropy, we had only one anisotropy axis. Here we have three. U1, so as input parameters, you give the anisotropy constant K in joules per meter cubed, and you give two axes actually, because the third one is computed as U1 cross U2. So there are three input parameters when you want to define cubic anisotropy. This is the formula when M1 and M2 and M3 are basically the projections of M on U on the anisotropy axes. So yeah, if we have a magnetic moment which is misaligned with all three axes, and then we relax the system, cubic anisotropy wants to stick it to one of those three axes. Again, if we start from a random configuration in animations, we're going to see magnetic moments pointing in all three directions, positive and negative. Okay, so far we had a look at the Zeeman, at uniaxial anisotropy, which can have two different characters, easy plane and easy axis, depending on the sign of K. And we had a look at the cubic anisotropy. And those energies are local, which means that magnetic moments don't care about their neighbors. They just care about the external factors, such as the anisotropy axes and external fields. Now, the exchange energy is the first energy we're going to have a look at, which is not local, but this energy is actually short range. So each magnetic moment sees its neighbors, and magnetic moments want to be parallel to each other. The parameter is A in joules per meter, and this is a scalar. Now, there are three different equations you usually see in papers. So there is this one, which is AM dot Laplace of M, where the Laplace we compute this way here. But usually you see this form. So this form is nice because the effective field is easy to see from here. It's Laplace of M. Then you usually see this form in papers, but most often you actually see this form, which I never understood. It's just a convention where we take a gradient of a vector field and then we square it, and then we somehow end up here. So if you see this and confuses you, it's just a convention to write it this way because this is too long. Now, one important thing to mention here is that we're talking here about ferromagnetic exchange. So that means that neighboring magnetic moments want to be parallel to each other and not anti-parallel to each other, like in antiferromagnets. This is important to mention because we said that micromagnetics is a continuous approximation. We want magnetization to be nice and smooth, and antiferromagnets are anything but smooth. So using negative A in simulations is not actually justified. There are many papers where people do that. It's actually everywhere, but it's not the best thing to do. There are proper ways of simulating antiferromagnets in micromagnetics using sublattices. But yeah, putting a negative A and just forcing the simulation is not a good thing to do. Yeah, quick simulation. So we start from a random state, and then in the end, all magnetic moments are going to be parallel to each other. We don't know in which direction. So they're going to choose the direction. So yeah, it's important they're all parallel to each other. Now, a little bit on Dzieloshensky-Moria. Here I'm starting with atomistic, it's easier to understand from the formula what happens. So again, when we look at this, let's ignore this sign here for a bit. So if we look at this, it's a vector D, which is a material property, dot cross product of two neighboring spins. Now, this is a mixed product here, or a triple product. I don't know how it's called in English. So we have dot product and cross product, and this is basically the volume that three vectors, the volume of the space that three vectors make. So if we had a minus sign here, this is, or plus or anything, so we're looking when this is at its maximum, and it is at its maximum when three vectors are all perpendicular to each other. So we can think about it and this way, let's say. So we have two spins, S1 and S2, on two neighboring atoms. And we have a D vector which is along the direction from one magnetic moment to the other. So from one atom to another. This is this is crystallographic class T or O, or usually we call it just the bulk DMI. This comes from the lack of inversion symmetry inside in the crystal lattice of the material. And now you see that the DMI wants to lie. So S1, let's say it's up, and S2 here, it's towards us. So all three vectors are perpendicular to each other. And the magnetic moments, they rotate in the plane, which is perpendicular to D. So in this case, if we had interfacial DMI, and interfacial DMI is we get it in thin films deposited on some heavy, like platinum, deposited on top of other materials. We get a D vector which is actually in plane, but it's perpendicular to the distance vector between two magnetic moments. And here you see that magnetic moments now are also 90 perpendicular to each other, but now they rotate in a different plane. Yeah, I'll go. Maybe it's going to be a little bit more clear here, and here we're going to explain the sign. So as I said, DMI wants two neighboring magnetic moments to be perpendicular to each other. Input parameter, so now we are in continuous limit. So parameter is D in joules per meter cubed. So this is a scalar. So when you take this equation here, atomistic, and you place that D is a scalar times the distance vector between two neighboring atoms and do the derivations, you are going to get this form. So it's dm dot curl m. Now, there is no clear convention should there be a plus or a minus. So there are some papers there is a plus, in some papers there is a minus. What the sign means, it just changes the chirality. So if we have two magnetic moments and we have a D vector which goes from one atom to another, so we can write it like this. Now, if D is, let's say, positive, so then D is in this direction, we get one vector up, another vector towards us. If the D was in a different direction, we change the way we change the rotation. So if one is up, then one is in plane from us. Yeah, and now here for the DMI, if we run a quick simulation, now it's a little bit difficult from here to see what's happening because camera is looking at the middle, but here you can see that neighboring magnetic moments are actually perpendicular to each other. Now let's look at the CNV. This is called interfacial DMI, and this one is responsible for nail skyrmions, and the previous term I mentioned is for Bloch skyrmions. Same story, just a different form. So now if we write the DMI vector like this, so it's in this direction like here, and we do the derivations, we get a different formula. Same story, as I said, magnetization rotates in the plane which is perpendicular to D. So now the rotation is like this, up to the right, up to the left, depending on the sign of D or the vector D direction. If we run a quick simulation, wait for it to end. So we're going to get, so basically we can't see much from here, but we can see that this vector is perpendicular to that, perpendicular to that. So they're all neighbors are perpendicular to each other. Now DMAG is a little bit too complicated to go through today, and it's a lot of maths, and this is the one which makes life difficult. In micromagnetics, it is a long-range interaction. So magnetic moments don't feel only its neighbors, the magnetic moments feel the neighbors in the distance. We can think about it as basically just a magnetic moment feels the magnetic field from all surrounding magnetic moments. This is a term which is computationally very expensive. And if we have time, I will put more details in for the next sessions. Okay, let me quickly go through. We have a few more quick slides, and then we can go on we can have a quick 5 minutes break. Now, the interesting things happen when we actually combine. So in the energy equation, we have different terms. So let's say we have exchange and Zeeman, probably the simplest combination. Exchange wants all magnetic moments to be parallel to each other, and Zeeman wants them all parallel to an external field. We can make them both happy, so no compromise is needed. So if we start from a random state over some time, the magnetic moments are all going to be aligned. Parallel, which means exchange is happy, and parallel to external field, which is here applied upwards. And yeah. Now the difficulty is, that's when the interesting things happen, is when we have energy terms that want different things. So let's say we have exchange and we have DMI of T class. So T crystallographic class is the bulk one. So the question is, can we have neighboring magnetic moments parallel to each other and at the same time perpendicular to each other? So we can't make them both happy. So the energies have to compete and reach a compromise. And now we think about it like exchange wants a 0 angle between neighboring moments. The DMI wants 90 degrees angle. And what is the compromise? The compromise is some angle between 0 and 90 degrees. And that's when we get a helix. Here you can see nicely the angles between neighboring moments. Now, we can have a look at the even more complicated case. Let's say we have Zeeman and anisotropy and exchange and DMI, and we start from some weird random configuration and we relax it, and we end up having a skyrmion. So this is a T class DMI or a bulk DMI, so that's why we get a Bloch skyrmion here. Yeah, we're going to have a lot of exercises with skyrmions later. Now, dynamics equation, as I said, so we had a look at the magnetization M. What is it? Just to repeat quickly, continuous magnetic field, infinite differences. We divide the space into small chunks. Each chunk has a single vector assigned to it. We had a look at the energy equation. Energy equation is the sum of individual terms. Those individual terms we just had a look at: Zeeman, anisotropy, DMAG, exchange. And now we have dynamics equations. So how does the magnetization want to change in order to minimize its energy or to interact with some external excitations such as spin polarized current or things like that? So we can think about the dynamics equation again just as a sum of individual dynamics terms. Each of those terms can be a function of magnetization field, of effective field, and some other external factors such as spin polarized currents. Or again, like an energy equation, this is something you have to define. So you as a physicist should decide what is in my micromagnetic system, what do I want to model, what the material parameters are. So this is something you decide. Now, what is the effective field? The effective field is basically a first variational derivative of energy density. So this is the energy equation we had a look at earlier with respect to M. And we get a vector field, which is, we call here H effective. Now in blocks, from the energy density we computed using energy equation, we take first variational derivative, we get effective field, which is a vector field, and then we put both effective field and magnetization into our dynamics equation, and we get dm/dt. And this dm/dt is something we use. So from this dm/dt, we know how to update the magnetization of our system in order to minimize its energy. Quickly, just two terms, precession. This is the form minus gamma naught m cross h effective. So the parameter is gamma naught. Now, this is something that's usually confusing. So if you Google for a gyrotropic ratio, you're going to get, I think, 1.70 something times 10 to the 11, but you put 2.21 times 10 to the 5. And when you think about this, gamma naught is actually just mu naught times gamma that you put in simulation. So if you find gamma, the gyromagnetic ratio of an electron in its value, you multiply it with gamma naught and you multiply it with mu naught and you get gamma naught. So here we know if this is the effective field and this is magnetic moment m. From these cross products, it's easy to find that it's going to go this way and then precess. So from in the animation, it looks something like this. So this is the side view and this is the top view. As the name says, just precesses forever. Now Gilbert damping, this is a term which makes m align with effective field. So it wants m to be aligned with effective field. The parameter is alpha. So this is something we say to ubermag, and it's computed like this. Now here this is a little bit messy to see. How do you know then it's going that way? It's going to be clear in the next slide, but a boring term just wants magnetization to be aligned parallel to the effective field. One thing here, alpha is positive. It's on the order of, I don't know, from 10 to the minus 5, 6 to 0.1, 0.5 or 1. So it's a pretty small value. Usually some micromagnetic simulators, when you say relax, they don't use conjugate gradient methods. They just run simulation with LLG, but put large alpha and turn off precession. Now, if we combine those two terms together, we get something called an LLG equation. And this is the precession term we had a look at in the previous slide. This is the damping term. Now, what we don't like about this equation is computationally we don't like it because we have dm/dt on both sides and we would like to have dm/dt on the left. So that's why when we do some gymnastics with derivations, we end up having this term. And here you can see what the direction of the damping is. So why damping wants to align with m with h effective. And here now, basically just the total dynamics is just the sum of precession and damping. So if we sum precession and damping, we end up having something like this. Okay, quickly through the micromagnetic simulator, and then we're going to have a break. So now we had a look at some building blocks. This is an oversimplified simulator. So things are much more complicated in real life, but I find it useful just to explain. When you run a simulation, it's usually good to understand what's happening in the background, and that gives you some understanding how to set up your simulation. And when you get certain errors, then you understand what they mean. So let's say we start from the magnetization M. So this is a vector field. And from that vector field, when we put that vector field into our energy equation, so this is our energy equation, we get a scalar field, which is energy density. Now, what we can do with that energy density, we can integrate it over the whole volume and we get a single number, a scalar, which is the energy, or we can take the first variational derivative of it and we get an H effective. And now H effective together with M, we put into the dynamics equation and we get dm/dt. Now dm/dt tells us how does the magnetization want to change in order to lower the energy of the system. So when we drive the system, we multiply this dm/dt by some time step we choose, and we get delta m. And then we update our magnetization. And we go round and round and round. When does it end? When m cross h effective, it's obvious maybe from here. So when m cross h effective is 0, or within some tolerance, of course, that's when it ends, and we know the system is relaxed. That's yeah, that's the minimization driver. OOMMF is a little bit more clever, but that's the minimization driver. Or if we run it using time driver, we're going to say run for 1 nanosecond in 200 steps, so we know what the time step is, and when we reach the final time, it stops. We don't know if the magnetization relaxed, we just know we ran it for a certain amount of time. Okay, so this was absolute basics with for micromagnetics, which is, I think, enough for the first session. And I would suggest we have a 5 minutes break now.
Yes, so let's take about, let's take a 4 minutes break. So we'll meet back at 1 p.m. US Eastern Time.
Yeah.
Thank you. Okay, fantastic. Marianne, it's yours.
Great, thank you. So I hope I'm sharing the right window. Yeah, so now we are going to do our first simulation with ubermag using OOMMF in the background. So I'm in the workshop repository, and I clicked on binder link just so to show you what is around, and you are familiar with, to make sure you are familiar with Jupyter notebooks. So when you open the binder session, you're going to get something like this. So this is an index notebook that we use just to summarize all the information for each session. But this is a Jupyter notebook environment. Few things to know is that here when you go to File, and you can choose the new notebook, we use Python 3. And when you work, yeah, let's actually open one notebook. So when you open a new notebook, it looks like this. If you want to change its name or the file name of the notebook, you click here, and we can say our first notebook, and you change the name of your notebook. You think about the notebook basically as a collection of individual cells. This is one cell here, you get it there by default. And you can change the character of the cell. It can be either markdown cell or a code cell. So markdown cell, you change it here, and here you type the text. So you can type some text. You can make some headings. You can make some subheadings. You can type LaTeX equations. So in $signs, B plus C, let's say. Or you can have display equations in $signs. So you can say, I don't know, gamma naught. Now, when you want to execute a cell, you hold Shift on your keyboard and press return. When I say return, it means enter on, for those who are in Windows. Or you can press this run here. Now, this is a code cell. We get it by default, and this is where we type our Python commands. So if I type 1 + 2 and press Shift return, so we always run the cell the same way, or let's click here just so you can see, we get the output here, which is 3. So this is the notebook's basics. Few things to remember is when you are inside binder and you leave the binder session, because everybody can join binder, you don't need an account or anything. but when you leave, everything you had is destroyed. So to make sure you have your notebook on your machine, you download it. So you can either click here on download and just downloads the notebook to your downloads directory if it's that's your default, or here you can download it as a notebook as well, or you can choose to download it as a LaTeX file or as HTML. So that's important. And then when you open the new binder, then you can upload the notebook. Then I think it's very intuitive. Sometimes what you need to do is you need to restart your kernel. You can do that using these buttons here, or you click on kernel and then you make it more obvious. So which means like you have a really long notebook and you don't want to go to the beginning and hold shift and return to execute all cells again. You can just go to kernel and say restart and run all, click here, then it's going to execute the whole notebook again. Yeah, I think that's pretty it. There are lots of tutorials online on notebooks, how to use them, and YouTube videos from conferences. So you can have a look at them. Explore these buttons a little bit. I find this quite useful when I want to put this cell below that one. So to swap the position, I click on this one and then I swap two cells. Yeah, have a look, explore a little bit. What matters the most here is what we type into these cells. Okay, so for that, we're going to go to our first ubermag simulation. So the goal of this notebook here is, as you see, the notebooks are already written and executed. They're already there just for me to save me time, because if I type all the commands during live sessions, it would take me 2 hours instead of 1 hour to go through the notebooks. So they're pre-prepared. As I showed you, there are markdown cells. So when I double click on this render text, I get the code I used to generate the text, and with shift return, I just render it. So now let's start with our simple ubermag simulation, just so you can see how does ubermag look like, how to write, and yeah, what is the ubermag, how does it look like inside Jupyter. Very basics again. So ubermag is basically just a meta package. So it's just a convenience name when you install the package, that it installs many different packages in the background. So ubermag is a collection of 6, 7, 8 different packages. Each package has its own responsibility. Now, why did we decide to divide it that way? So if we think about discretized field, so it's a finite difference field, and discretized field package basically defines those fields, boundary conditions, does the operations on fields, etc. It's not tied only to micromagnetics, so it can be used in general finite difference code. So that's why we like to keep it separate, and people who don't want to do micromagnetics, who want to do, let's say, computational fluid dynamics, they can use the package in the and micromagnetic models and things like that. So it looks a little bit complicated, because you would probably think I need to just import ubermag and that's it. But most of the time, you're just going to use you're going to use minimum 3, maximum 5 packages. So you just need to learn 5 different names, and I think they're quite intuitive to remember. So let's start by importing 2 things. So in Python, to import a package, we say import and then the name of the package. So let's ignore here the rest of this line. So now import imports this package. When you run conda install, this package was installed. And now whenever we want to refer to this package, so we want to call something which lives in this micromagnetic model, we would have to type, let me just go here, we would have to type micromagnetic model dot, and then, I don't know, exchange, let's say. So this is a little bit too long for me to type and I'm lazy. That's why we type this as. So import micromagnetic model as MM. So whenever I need to refer to micromagnetic model, I just type MM. So mm.exchange. The same story for discretized field. So these are just short names for this, so we don't have to type. Okay, so we imported two things. Discretized field is responsible, as the name said, for magnetization. Micromagnetic model is there for defining the model. So energy equations, dynamics equations, systems, etc. So the first thing you do is you define the system. So the system is like an umbrella which consists of three parts, of three components. One component is the energy equation we discussed earlier. Another component is the dynamics equation, which is optional, but will become clear later, and the initial magnetization. So if you remember our algorithm I showed you before the break, these three things you as a user need to define. Now you can ask, where does the sample go? Well, how do you know, is it a sphere, or do you have boundary conditions, etc.? That all goes to M. So you define the field, and then you give the field to the system class, to the system object, and then it extracts everything it needs from there. So the first thing we do is we define our system object. This is a simple Python assignment. What is on the right-hand side, put to the variable on the left-hand side. So mm.system, if you remember, mm is what we imported here. mm.system, capital S here. So all classes start with capital letters. And here in brackets, we give the name of our name, we give a name to our system. Now, this is something you should choose cleverly, because okay, I get complaints about my font size. Let me try to make that larger. I hope this is better now. Maybe it's too large. I hope this is better. If not, then please complain again. Okay, so this is the name of our system class. Now, ubermag communicates with calculators via files. So oomph gives us, so oomph gives us the files, and then we need to read them. So we communicate through files. And when you define the system and you run the simulation, a directory with this name is going to be created on your machine. So it's like oomph. When you run a simulation, you get lots of files as an output. This is a very similar story. So choose these directory names with some meaningful names. This can be any valid Python variable name. So spaces here are not allowed, or you can't start it with a number. So just anything that can be a valid variable name. Yeah, let's speed up a little bit. Now we define the system. For system, we have to define three things. So we have to define the energy. Energy first, let's say. So our system has three energy terms. It has exchange, it has Zeeman, and it has Dmag. As I said, you as a physicist decide what you want or what you need. So exchange, this is the exchange constant, and Zeeman, this is the external field. And here we define those two parameters. I forgot to say, in Python, when you use hash and then you write something, this is a comment, so it's completely ignored by Python. It's just for you to understand what you wrote later. Now, A is 10 to the minus 12. So I hope this is obvious. So when you see E, you read it times 10 to the minus 12. So this is our A. It's all in SI units. So if we couldn't, so it's in joules per meter. And now H is a vector. and we need 3 values. So this in Python is called a tuple, and it has 3 values separated by comma, and this is basically 5 times 10 to the 6 amps per meter, 0, 0. So we only have X component. How do we define the energy? We say system. So this is the system object we just created. So here, if we used, I don't know, a model instead of system, then we would have to use model here as well. So this system has nothing to do with that. This system is this thing here. So everything on the left-hand side, you choose the name. And we say system.energy equals, and then we just put the sum of individual energy terms. So we say MM, which comes from Micromagnetic model we imported earlier, dot exchange. Remember, all classes start with capital letters. And A equals A. So we say into the parameter A of, for the parameter A of exchange, use this A. And this A on the right-hand side is the one we used here. Usually these things work as well, but it is not a good thing to do. So please always be explicit and say A equals A. So it means this A we define here assigned to the internal A of exchange. Then we say plus, another term is DMAG. We don't need parameters for DMAG. And the third term is the Zeeman, so H is H. We define here, and it's a vector. So as you see, oh, I didn't run the cells from the beginning. So I need to run the cells. So shift return, shift return, shift return. And now we define the system energy. So you can see single line. Now we want to define the dynamics, let's say, and we want to have an LLG. So we have 2 terms, precession and damping. For precession, we need gamma naught. And for alpha, we need, for Gilbert damping, we need alpha. So I have these 2 values. Now, there are lots of default predefined constants in ubermag, so you don't have to type gamma each time, but I'll show you that later. And now you say system.dynamics, and on the right-hand side, you just write the equation. So you say mm.precession with gamma naught equals gamma naught, and this gamma naught is that one here, and mm.damping, and we need to give alpha to it. I hope this is not too complicated. So now the initial magnetization. So we defined energy, we defined dynamics. So how do we define initial magnetization? So there are 3 steps basically. The first one is to define the region. So the region is basically Atlas in OOMMF. Later, I'm going to show you a few shortcuts so you don't have to type that much, but I think it's nice to be explicit in the beginning. So we say DF is discretized field we imported earlier, dot region, capital R, and then for the region we need to give 2 points. So 2 points, maybe let me just split this cell and, okay, so we define the region and we give 2 points. So 2 diagonally opposite points in the sample. We can choose any, but they must be, of course, diagonally opposite. This is going to complain if you give a region which has 1 dimension to being 0. So if we put, let's say, this, we would get an error message telling us that one of the region edges in the x direction is zero. So we need, this is the error you can get, pretty simple. Now, yeah, don't worry about this command, but this is a quick view of the region we just defined. So it is a 50 nanometer edge length cube. K3D is a quick 3D visualization for objects. So if you do region.k3d or mesh.k3d, you get this quick interactive plot. And here we see the region we just defined. So we get nanometers on the axes, and we can check, is it the right one? So we can see that this corner here, maybe if I zoom in a little bit, zoom in a little bit, we can see that this corner we defined here is actually at 0. That one is at 50. If I move it a little bit. Yeah, so this is the region. 2 points and you get the region. Now, this region we defined here, we need to give to the mesh. So what is the mesh? Mesh is the region plus discretization. So now we are dividing our sample into small chunks. There are two ways how we can do that, but now for simplicity, I'm just going to show you how to do it using n parameter, and n parameter is just the number of discretization cells. So you say df.mesh, capital M, and then you say region equals region. Region is the one that we defined previously, and here you say, please divide this region into 10 cells in the X direction, 10 cells in the Y direction, and 10 cells in the Z direction. So we're going to have 1,000 cells in total. And maybe quick look here, mesh.k3d. We get something which looks very, this is our region, and now this visualization just gives us the size of one discretization cell. So just we get a feeling, is it small enough, is it large enough, did we forget to put times 10 to the minus 9 or something? So this is a quick check. Okay, and now the final thing. So we define the region, we define the mesh, and now we need to define the magnetization. And magnetization is just is a field object. So again, discretized field dot field. And for the field, we need to give the mesh, and this mesh is what we define here. Then we need to give the dimension. Now this is a little bit confusing, and it's our fault. We should have called it value dimension when we started ubermag, but we called it dim because, well, yeah, for some weird reasons. Yeah, but this is the dimension of the value. So if you have a scalar field, you put 1. If you have a vector field, you put 3. So this is basically how many numbers are stored per cell. So for vector field, we stored 3 numbers per cell for each component. So this is dim is actually value dim. And here we set the value of our field. So in the next tutorials, you can put many different things here. So you can put files, you can put functions, another fields, lots of different things. But now for simplicity, we just pass one tuple or one vector, which means all the cells in my field are going to have the same value, and it's going to be this. So it's going to be 0, 1, 0. Now, if we define the field like that, we would get the field which is actually 0, 1, 0 at each cell. But now in micromagnetics, we need to pass MS, and this is the time. This is the place where you need to define that. Again, MS can be lots of different things. It can be functions, it can be files, fields, whatever. It's important that it's a scalar. It is always a scalar, of course, and then you pass it to the norm. So you pass MS to the norm, and now when you define the field is going to be normalized to MS. So its values are not going to be 0, 1, 0, but it's actually going to be 0, MS, 0. Now, a few quick things just to, which can be useful. So here, if you say system, which is the object we define, dot energy, we defined here as a sum of 3 terms, exchange, DMag, and Zeeman. You can just run that in Jupyter, and then you are going to get a human readable equation. So you can have a quick look of, is my equation right? Did I define it as I wanted? And the same story for the dynamics. So this, you can see, this is actually the LLG in its explicit form, the dynamics, and then we have already had a look at these things. So, but here I put it here just to show you a few things. So when you have a system object, and in system we defined M, which is this field here. So this is where we defined it. You can just keep going. So you can say in system object, give me M, and from that M, give me the mesh, and from that mesh object, give me the region, and from that region, give me K3D. And now it's going to plot the region. So you can, with these dots, you just go in. So you access different attributes or methods from different objects. So we can visualize the region, we can visualize the mesh. We had a look at this plot. And now this is a quick, I haven't showed you the 2D plots earlier. This is how to plot the plane. So to plot the magnetization on a 2D plane using matplotlib. So what you do in the system object, give me the magnetization and then dot plane. This means cut our sample. So our sample is a cube. Plane Z means cut our sample with a plane, which is perpendicular to the Z-axis and goes through the center of the sample. So if I set Z equals 25 nanometers, I think that was the value. If I set this means give me a plane Z equals that. So this is basically an equation of the plane, or a plane perpendicular to the Z-axis. If I'm lazy to type, and most of the time we're just interested in the sample in the middle of the sample, I just put this, or I can ask what is along the X direction or along the Y direction. So I'm looking at the Z direction. Now, if I comment this out quickly, now you can see that when I do this, this gives me just another field object. And from this field object, I can again keep going, saying mesh dot region dot blah, blah, blah. Okay. Okay, font should be larger. I hope this is fine now. Can you check quickly? Great. So yeah, but we're going to have a look into this in more details. So when you see these long commands, you don't have to think like, okay, if I want to plot something, I have to type 15 things separated by dots. This is quite intuitive, I believe, and we're going to have a look into that later. Now, if you remember, we initialized our magnetization in the positive Y direction. So 0, 1, 0, and we look at it. So it's basically going upwards. Now, on 2D plots, we see the magnetization. So we see the in-plane magnetization component. So each vector here is basically the X component of magnetization and the Y component of magnetization. And the color is the Z component. Now the Z component is boring. It's always 0. So we are here, we don't see it. Again, visualization is quite powerful, and we do it in the third session because it deserves more attention. Again, you can plot the fields using, so now I'm doing the same thing. So this is the same. I'm not just saying K3D vectors. And here I adjusted the head size. Again, something we're going to have a look into in the third session. And I zoom in and I see that for each, we can't say atom here, but we can say, okay, for each discretization cell. So this point here is the center of each discretization cell. We can turn the points off, lots of ways to customize the plot, but you can see it, so you see it in 3D. Okay, so what did we do so far? We defined our system object using micromagnetic model and discretized field packages. In the system object, we set up the energy equation, single line, not difficult. We set up the dynamics equation, another single line, not difficult. And the third thing we define is the magnetization field, and that is a little bit longer, but there are certain tricks how to simplify it. And this is where the magic happens. So far, we haven't used any micromagnetic code. So we're just using pure ubermag for defining these things, equations and everything. But now when we want to drive the system, this is the place where we import a specific calculator. So for OOMMF, the calculator is OOMMF-C. For MuMax, the calculator is MuMax 3C. as I said, MuMax is for our third session. Don't try it yet, but it's everything, as you see, everything before is going to be exactly the same. So we import UMFC, and now we can say here, okay, why it's MC? The reason we use MC here is that if you want to change the calculator later, you don't have to go through the, if we called it OC, then you would have to go through your entire code and change OC to MC if you imported MuMax 3C. But if you, so we keep it MC so that it is micromagnetic calculator, MC, and here we import the calculator we want. So basically, this is the where all the magic happens. If you want to use MuMax instead of UMF, you just change this one thing to MuMax 3C. And that's it. Everything else stays the same. Okay, so we import UMFC. This is the calculator. And this is a package which knows how to talk to UMF. So this package knows how to take out, how to translate our micromagnetic model we defined earlier and translate it to a language UMF understands. So this writes tickle files and communicates via different files with UMF. So this is the package that does that. So we import UMFC as MC, and then we define the driver. So here we're going to use the minimization driver. So this is the driver, if you remember from the algorithm, is going to keep going until M cross H effective is 0. So we say minimization driver, we create that object. We say MD, minimization driver. You can give any name, of course, equals MC.minDriver. And then you say MD.drive. So using this driver, drive the system. And then you execute this cell. Now you see at this point, UMF is being called, it's run, and now that's it. From now on, what happened is that in our system object, magnetization M is now updated. So M here was in 0, 1, 0 direction, but now it's something else. So when the driver is done, M is updated. Now, lots of different information is there. You can say, yeah, the .data, no, sorry, .table.data, that you can access different things from, what did I, sorry, it's system.table, yeah. So you can get different, so these are ODT files that are created, so, but data analysis and that kind of stuff is for later. But everything you need is in this system object and you access it via these dots. So all the files UMF created, we read them and they're saved somewhere inside system object and you can access them. Okay, now let's have a look at the magnetization. So now we plot the magnetization. So what do I plot here? I say system object, give me the M. Now M is the relaxed magnetization. Cut it with a plane, perpendicular to the z-axis through the middle. And now this is, I smuggled this in, just we teach a little bit in each cell. This means if I don't put this, I get basically the same thing, which means 10 cells in this direction, 10 cells in that direction. So this is the discretization we used. But here I can change that by passing, okay, we say, okay, we have too many arrows, so I can say 5 by 5, and then that's how you change the size of, this is how you change the discretization. And now you can see the magnetization. Let me put this back to 1010 so we can see it a little bit better. So we started with this, everything upwards, positive Y direction, and now everything is to the right. Now, why is it to the right? If you remember from our energy equation, we had Zeeman field. We had Zeeman field here, which was applied in the X direction. Very simple, just to demonstrate you some basics. Yeah, and that's it. Now we can do the same thing for We can plot it as a vector field here. And we can ask what is the average magnetization. Now M by default is a full M. So lowercase m dot ms. If you want to get a normalized field, not for M, for any field, you type system dot m dot give me the orientation field. And now this is just a new field here. And anything you can do with fields, you can do in this as well. And you say average. And now if you put this average, we say that the average is in the X direction. Okay, so this was 1 hour and a half. I can now, yeah, so the time is up, but I could use another 5-10 minutes to go quickly through Python basics, if that's okay.
Yes, please go ahead. We have more than 90% of people staying, actually.
Okay, I will go
and it's recorded anyway. Yeah.
Okay, for those people who are familiar with Python, you don't have to go through this. This is just some quick basics. As I said, you don't need much Python. You saw basically most of the commands we are going to use in ubermag we just saw in the first notebook. So you won't need to know much of Python, but more you know, the more confident you are in writing simulations. So Python basics. Variables. As I said, when we said system equals mm.system, what does it mean? What is on the right-hand side? Put it to the left-hand side. So this is not mathematical equals. This is assignment. This is mathematical equal. This means what is on the right-hand side, put into the left-hand side. Now, Python is a dynamic language, which means you don't define variables like in, I don't know, C++, where you have to say, this is going to be my integer and it's never going to change later. Here you can change the type of the value. So we say a equals 10, and then we can ask what is the type of a, and then we ask what is the type, we get it's an integer. How does it know it's an integer? It's because there are no dots here. If we had this, then it would have been float. So these are called literals, and literals with dots are floats by default, and without dots are integers. In Python 3, you don't have to worry much about this. In Python 2, it was tricky. When you divided two integers, you got an integer. Now in Python 3, you get a float. So we have integers, we have floats, we have strings. Strings can be in single quotes or double quotes. We have tuples. So far we saw tuples when we defined vectors for fields. So tuples are just some elements separated by comma inside rounded brackets. It can have 3, it can have 4, 5, 1 element. So we use 3 because we are in 3D space. Tuple, and we can have a list. List is the same thing as a tuple, just in square brackets. There is a small difference between those two. I'm going to show you a little bit later. Yeah. Why is my cell? Okay. Large, small values. We had a look at this. When you see E, it means times 10 to the minus 6. So this is 2.1 times 10 to the minus 6. You write like that. When you want to ask for a value, so if I did this, I get nothing in Jupyter, but if I say just give me A, it gives me A. And now I get this output of a cell. Basic operations quickly. Plus, minus, times, division. If I divide two integers, 5 divided by 2, I get a float. How do I know it's a float? Because it has a decimal point in it. In Python 2, you would get 2, so it would cut out this. Power, this is a little bit different. So people are used to write powers like that with a hat. In Python, it's this double star. So this is 5a to the power 3, it's 125. A little bit more complicated operations. So if you're looking for sines, cosine, logs, complex numbers, Fourier transforms, yeah, most of these things live in other packages. So basics are in math, so you can say math.sine and then you compute sine of theta. Oops, yeah, this is what happened. I forgot to import. Math sine of theta, this is a pi with as decimal points with 5 numbers after the decimal point. I managed to remember. Cosine, same thing. A bit of sine, so pi, you get like this, math.pi, log, E is like that. A little bit about lists and tuples. We said this is a list, we said this is a tuple. What is the difference? The difference is in the brackets. Now, how do we do indexing? So if I want to get the first element of my list, so this is my list, I want to get the first element, so I want to get only this one. I say A, and then in square brackets, I put the index. So Python indices start from 0. So this is element 0, this is element 1, 2, 3. So if I say A of 0, it's going to give me the first element, which is 1. Now, if I want to change the value, I can say A of 0 is 5. And now if you can run it, you can see that I replaced 1 from here with 5. B of 3, give me not the third, it's the fourth element because we start from 0, but this now from the tuple. If you want to read the last element, you don't have to remember how many elements do I have, -1, and then put it as an index. You just put -1, and that means give me the last element. So these two things are basically equivalent. Length, you can ask what is the number of elements in my list. Now, what is the difference? So B is a tuple, if you remember, and I say I want to change the third element, not the second, the third element to be 3. And if I run this, I get an error, which tells me that you can't do that because tuples cannot be changed. So this is the main difference between. So tuples are not mutable, you can't change them. Once you make them, they stay like that forever. So this is the whole difference. A list, you can do whatever you want with them. You can delete elements from them, you can add elements. Unpacking, this is something we're going to use when we write functions to define different geometries. So if this is my tuple with X, Y, and Z component, let's say, and now I want to split it into 3 parts. So if I want to write an equation with the X component, Y component, I would have to say, okay, point 0, which is the X, times point, and it takes a long time to write that. So the quick way is you assign the first element of point to be X, the second to Y, the third to Z. And now if we print it, you get it like this, but more convenient way is just saying this. And this is tuple unpacking. So the first element from point goes to X, the second to Y, the third to Z. And this is the same thing. Adding an element to the list. This is our list, dot append, and here you put a new element, and then we print the output list, and then we get, it's a little bit slow, yeah, and then we get a new element appended to the end. Dictionaries, we're going to use them when we define spatially varying fields and spatially varying parameters, when you have different layers, different materials, different layers. We're going to use dictionaries. So if you want to say, okay, exchange constant in my region 1 is that, you write it like this. So you put a string with a name. It doesn't have to be a string, but we're going to use strings. You put a colon, and then you put a value, comma, key, colon, value. This is a dictionary. How do you read a dictionary? You read it like this. So you put D, and then instead of a number, which we use for tuples and lists, we put a key, and this is the key. Quick selection. That's a if statement. So pretty simple. If, and here you put your conditions, colon in the end. And if this is true here, you're going to do all the lines which are indented with respect to that line here. So maybe you are used to having this, and then you don't worry about indentations. Python doesn't have that, so you have to worry about indentations. So you write something, and everything that belongs to that and that is going to be executed, you indent. So here we say if A is 5, which it is, and B is less than 10, which is true, you're going to do these two things. So you're going to print I'm in, and you're going to increment A by 1. You print it, and that's it. Same story here. If you have multiple things, you say if something, and then elif is else if, and then in the end, if none of these two are true, you run the else. So here we end up here. Iteration, for loops, we're not going to use them much, but this means run this line here by replacing I with elements from this list here. So if I run this, it's going to print. It's a little bit slow today. I don't know why. It must be the binder must be busy. Yeah, but let's keep going. Same story. If you want to index by element, this we don't use that much. This is a little bit bad Python, but sometimes you need to do it. So if you want to iterate through indices, you write it this way. Same story here. And this is, yeah, functions. You define the area. So you define the function, you start with def space function name, and then in brackets you put the input arguments. So we want to compute the area of a rectangle. So we have two input arguments, A and B, colon, this is very important, and then the next line indented, and this is what the function is going to return. This return here is very important, so return and print are not the same. So if you get an output here, there is a difference if the value was printed or returned. Okay, so this is our area. This is a little bit more complicated function, which takes a list as an input and gives me the sum of elements. You can have a look at it later. Keyword arguments. So let's say our function has 20, 30 different arguments, like our plotting functions in discretized field. You can pass probably 100 different parameters, and now you don't want to type each of them. So we assign default values to them. So when you call this, minimum you have to pass is A, and then if you want to pass more, you pass more. So here we passed 1, which goes to A, and then these stay the same. Imports we discussed. We import something like this. If we want a shorter name, we add this. We add that. Common mistakes. You forget to put the colon here. So if you run this, you get a mistake. So you need a colon here. You forget to indent. So this belongs to this function. So it needs to be indented. Mixing types. So you try to say add 10 to A. This doesn't work. Then using an undefined variable. So when you get a message like this, it means Python doesn't know what it is. Or you're using something which is not imported. So here we're importing SciPy, and we want to use the FFT, the Fourier transform from SciPy, but we actually use this name. So yeah, I already mentioned this. In Python, everything is an object. So if you want to do something with objects, you say my object, and then you say dot, and then you can press tab, and then here you can see what you can access from that object. So if we did system.m.tab, and then you would see what is there, okay? So for example, if we said like here, my object.lower, then it would just put all those to be lowercase, so we'll get U changed. Getting help. When you are inside the Jupyter notebook, the easiest way to get help is just to type the function you want to use and the question mark. And then here you get the documentation for that function. with usually small examples. Everything in ubermag has this API. It is always up to date. So if tutorials are not up to date, I try to keep APIs always up to date. So when you get stuck and you don't know what it means, what you do is you do, I don't know, system.m, oops, you do system.m, and then you think what you can do with it, you press tab, and then you find what is in there, and then you say, I don't know, average, and then how do I call it, what do I do with it, put a question mark, and then you will get this documentation here which tells you what to do. So if there is something obvious you need to do, there are high chances it's already in ubermag. So by a little bit of pressing tab and looking at the documentation, you can find it, or you go to our documentation. Okay, so I will now stop sharing my screen and have a look if there are any questions. So there is one question: is m.orientation the unit vector field, or m divided by ms? If not, what it is? Yes, it is a unit vector field. So at each discretization cell in the field, we compute the norm, we take the vector from that cell, divided by the norm, and this is the value for that cell. So when you ask for m.orientation, then you get the unit field, so divided by its norm. Okay, that's what I wanted to show you for today. The homeworks are basically try to open Binder, try to run the first notebook. As I said, next two tutorials are going to be much more complicated, but not too complicated. We're going to go through some real simulations. So next session, we're going to define some complicated geometry, put a domain wall pair in it. Then we're going to push it with spin polarized currents, and then we're going to get Skyrmion. So we're going to do domain walls to Skyrmion conversions, and then we're going to look at vortex dynamics. So homework, try to install ubermag if you want to, follow one of our YouTube videos, try to run one of the notebooks, have a look at the slides if you want to. One thing I can mention here in the end, maybe if I quickly share my screen again. I left this from the previous workshop. So I showed you lots of equations in the slides and formulas. So here in extras, there is this derivations PDF. This is something I used as a, this is a scan of the notebook I used to derive different things, to practice a little bit of maths. So here it is. So if you are wondering how to get effective field using Euler-Lagrange for DMI, then it's on page 23, and how to derive, I don't know, this is a little bit of quantum gyromagnetic ratio. So why is it mu naught times gamma? Then you can have a look here. How to, different things you can have a look here, which might help you. So that's all I plan to show today. We are 22 minutes over the planned time. I apologize, but yeah, that's it.
Thank you very much, Marian, for this very informative tutorial. And so next tutorial will be the next Thursday at the same time. And please definitely try out this Jupyter notebook and try on some of the homework.